Okay, hello everyone. Um, Thank you for coming. My today's talk will be on decentralized optimization, and there is a general plan. Um I'll begin with some introduction and give some basic facts about decentralized optimization on time-varying networks, and then I'll present theoretical analysis and numerical experiments of the proposed method, and finally make some conclusions. We seek to solve some type problem in a distributed manner. What does it mean? It means that each FI is held separately by a computational agent, and the agents are connected by a network. There are two approaches, centralized and decentralized, and this talk is about the second one. In decentralized scenario, you have several nodes which are connected to each other by links, but there is no centralized server. Moreover, the specific case of this talk is a time-varying network. That means that from time to time, the edges in your graph may appear and disappear. This can be caused by technical malfunctions such as loss of connection between nodes. It's typical for wireless networks. Okay, so the proposed method is a specific variant of projected gradient descent, and that is how it works. Let us reformulate the initial problem and distribute the local copies of parameter vector x to every agent in the network, and add constraints on x1, etc., xn. That will lead to another problem, which is of higher dimension, but which is constrained. So denote x big the matrix of all x's over the network, and the columns of x will be stored distributedly over the agents. Now we are going to solve this problem. Yes, under some assumptions. That is, we want every Fi to be strongly convex, smooth. Smoothness means Lipschitz means having Lipschitz continuous gradient, and it is everything in the 2 norm over RD. Or since we are working with matrices, it's Frobenius norm in the matrix space RD on N. So since we are working with a constraint minimization, let us employ a simple method, that is projected gradient method. We do remember that K is the subspace defined in such a way. A subspace, it's a linear subspace of the matrices for which it holds x1 equals, etc., equals xn. Our methods will be just projected gradient on K, and on this linear subspace, function f has good properties. In particular, it is strongly convex and smooth with the following constants. It's strongly smooth, it's strongly convex with constant mu f. That is the same constant, which is the sum of mu i's. Actually, it's a better constant than maximum of mu i's. And the same holds for L smoothness. Okay, so we want to obtain such xn. We want to obtain an epsilon solution to the initial problem. That is the proposed method. Unfortunately, we cannot make the projection exactly, because we don't have a centralized server, and that makes us to employ some distributed method and find an inexact projection of the gradient step, of this gradient step. So the outer methods, the outer loop is just gradient descent, and the inner loop is a specific algorithm. Let us begin with the inner loop. We can replace the projection problem with such minimization problem and change the constraints using a Laplacian matrix, a Laplacian matrix of the graph, which Caesar talked about in his talk. Yes. Therefore, we need. That is how graph Laplacian is defined. On the diagonal, it has degrees of the corresponding nodes. It has minus ones on the points corresponding to graph edges, and it has zeros elsewhere. The main properties are as follows. It's positive semi-definite, and its null space is exactly our constraint set K. But as already mentioned in this talk, we're working with a time-varying graph, and a time-varying graph leads to a sequence of different Laplacians. So we're in fact working with a sequence of Laplacians, not with one fixed matrix. There is one more preliminary fact that will be used later. That's a fact about problems with linear constraints. Let us take a convex problem with constraints of this form and move the constraint into the penalty, how it will affect the solution. And then the answer is, on the next slide. If we choose Ry big enough, that is the minimum eigenvalue, minimum positive eigenvalue of the matrix. If we choose Ry big enough, then it holds that the solution of the penalized problem differs from the solution of the initial problem not too much. By not too much, I mean less or equal to R epsilon, where A is defined the following way. So if we introduce a big enough penalty, then we have a relatively small change in the optimum value. That is the key of our decentralized algorithm of projection, of finding the projection. Okay, let us return to the projection problem. And now we use the Laplacian properties to reformulate the linear constraints. And that leads us to a problem with affine constraints. And on the previous slides, we have just shown what we're going to do with it. We're going to add a penalty, which is big enough. It can be shown that by big enough, I mean taking R corresponding to this formula. And that leads us to a penalized function. But we remember that the Laplacian changes from time to time. So that leads us, in fact, to a time-varying function. And we're going to employ a gradient method on this very function. The good news are as follows. Since we add a penalty in a smart way, then the minimum point of hk does not differ too much from one iteration to another. The change is proportional to epsilon 2. So now we need one more additional assumption on the graph. It's not an assumption, it's just a definition. We denote theta max and theta min the maximum and the minimum positive eigenvalues of all WKs. And finally, there is the result that the minimum points of each case do not differ too much. They differ not more than A on epsilon 2, where A is defined the following way. Okay, so now we employ a simple gradient method with a constant step size on the projection problem with penalty and analyze its convergence. First of all, let us compute the gradient, and here we show that the gradient can be computed in a distributed setup. What does it mean? Remember that, recall that these matrices consists of columns, and the columns are held locally by computational agents. So in order to compute the ith column of the left-hand side, you need to know only the ith column of the right-hand side. These guys are already held at the ith node of the computational network, and the last summand can be computed the following way. Recall the structure of W, which is a graph Laplacian. And you will see that if you want to compute xw, the ith column of it, you need only to communicate with neighbors of the ith node. So the ith node can make a gradient step only by communicating with its neighbors. And one step of this method takes exactly one communication round over the network. So that is how we want to employ gradient descent, and it remains to show its convergence. First of all, note that this gradient descent, its trajectory lies in the subspace which is orthogonal to K. It can be easily shown by this, by this formula. If you take, by definition, you can take any z in null space of any z in K, and by definition obtain that this guy lies in orthogonal subspace to K. So the trajectory remains in the trajectory remains in K orthogonal. And finally, we obtain, using this fact, we obtain the final result. That is, in order to obtain an inexact projection, you need to make this number of iterations. This number of iterations is proportional to He, which is lambda max over lambda min. And He is a characteristic of the communication network. It does not depend on the function. And this result is logarithmic on 1 over epsilon 1. So by now we know how to find an inexact projection on K, and it remains to analyze the outer loop using this result. And the outer loop is just projected gradient method with inexact projection. And it can be shown that it requires this number of iterations. The number of inner iterations is incorporated in this result already. So there is L phi over mu phi. That is the ratio for the function f. Multiple by He, that is the characteristic of a graph, and multiple by square logarithm, by 2 logarithms of 1 over epsilon. This is the number of communication steps that is required to obtain an epsilon solution of the initial problem, of the initial minimization problem. And that concludes the theoretical part. Now we will move to numerical experiments and some discussions. We carried out experiments on a simple logistic regression problem. Of course, you can say that that this is a good problem, that it's a very simple classifier, and you're of course right. You will be right, but in our scenario, there are other circumstances which make this problem not so easy to solve. I mean that solving even this simple problem in a distributed setup on a time-varying graph is not so easy. So the toughness of the task lies in the communication setup, not in the objective function. And we compare our algorithm with another algorithm for distributed optimization, for decentralized optimization, called digging. Digging was proposed in 2017, I guess. And these graphs show that our algorithm heavily depends on the parameters. That is, by the red one, for example, the red plot shows what happens if we make exactly 5 iterations in the inner loop. That is 5 iterations for obtaining the inexact projection. And what happens if we make 25 iterations on the inner loop? And what happens if we make 100 iterations in the inner loop? And you can see that the more iterations we do, the more exact consensus we obtain. So that is the function value, and that is the distance, the accuracy of the projection. And you can balance between the accuracy of the projection and the function residual by choosing the proper number of steps in the inner loop. And these graphs show that digging algorithm outperforms us in the terms of consensus in all experiments. But sometimes we can outperform it in terms of the function residual. And
please explain what do you mean by consensus in this case, like for logistic regression? Because prior to that talk, for example, there was like another function that we want to minimize to find consensus.
Yes, by consensus I mean the following thing: we at each outer iteration we need to find a projection. So with some fixed accuracy. So after k iterations of the inner loop, we obtain some xk, and by consensus residual, here I mean the distance from xk to its projection on k. Probably it's better to draw something on the whiteboard.
I mean, the outer iteration is a projection gradient.
Yes, so there is xk, right? After that we make a gradient step. That is called yk. And then we find projection on k. K big, and find x k plus 1. And this accuracy, this projection accuracy, is plotted on the right plot.
It is the distance.
Yes, it's epsilon 1, and it is plotted.
The real projection.
Yes, and yes, here is the actual projection of yk. Of yk plus 1. Yes. It's the distance from the actual projection. But since here we run simulations, and we know the actual projection. So we can compute the distance from the actual projection and plot it.
And what do you mean by one iteration of this method? The number of gradients?
The total number of iterations, or the total number of communication rounds, including inner loop. Yes.
So here you're including inner loops.
Yes.
So how would it look if you only count outer loop? Like because the good thing with digging is that communication rounds and gradient computation is the same.
Yes. In our case, if we only plotted the outer loop, we would get a plot for a centralized method. Yes. And of course, it would be better than everything else. Here are just another experiments on another data set. These are all experiments on real data. And well, it shows pretty much the same results. So we can outperform other algorithms by choosing not too many iterations on the inner loop, but we lose in consensus distance, in consensus accuracy. Okay, now I'll talk about some extensions. And first of all, there are known lower bounds for distributed optimization on static graphs. And they write as follows. The square root of the function L over mu, the square root of a graph he, and logarithm 1 over epsilon. And in our case, we don't have an optimal bound, of course, because at least we are working on a time-varying setup, and obtaining lower bounds for a time-varying setup is an open problem. And we have much worse dependence both on the function parameters and on the graph parameters. The open question is, how can it be improved? Maybe we can accelerate the outer loop, or maybe we can accelerate the inner loop. And the interesting thing is that here we don't have L max and mu min, because we think it is a specific case of a non-accelerated method, because this ratio is better than this ratio without square root. So we think that this result is improvable to something like this, but not yet to something like this. It's left for future work. Moreover, recall, what does projection on K mean? It is just the projection of some matrix Y on subspace K is just a matrix consisting of arithmetic means of its columns. So in fact, our projection procedure is just finding an arithmetic mean as fast as possible. And if we worked in a centralized architecture, we would compute this projection exactly, because it's easy to compute the arithmetic mean. But we work in a decentralized case, and that leads to an inexact projection, or inexact finding of arithmetic mean. This can be improved as well, because for finding arithmetic mean, there is a special group of algorithms. They are called gossip algorithms. They use a matrix which looks like Laplacian, but has slightly different properties, and they are based on this iterative scheme. Well, in Russian it's called simple iteration. I'm not sure about the analog in English. Ну, короче, метод простой итерации вот такой. Вот. So these algorithms allow for different extensions, such as randomized versions, asynchronous versions, and more. And they can be employed to improve our algorithm as well. And finally, you can look at our problem at our method as a proximal method, where the prox summoned is just the penalty. And if you write a proximal method for this function, you'll get exactly the sub-problem which we solve in a loop. So this is this xk minus gradient step is exactly yk plus 1. So this problem is exactly how we do projection on k. And maybe different results in theoretical part may be obtained by using the analysis of prox method employed to our method. And yes, that brings me to the end of my presentation. Thank you for your attention.
Questions? I wanted to ask about the experimental setup. Carry out experiments on time-varying graphs.
Yes.
So at each moment of time, your graph Laplacian is different.
Yes.
So you just generate some random such random matrices at each.
No, I generate random graphs at each iteration, and for the graph I compute its Laplacian.
Mm-hmm. And what assumptions do you have on this?
On the graphs, we assume that every graph in the sequence is connected.
You just assume that they are all connected.
Yes, but it's a fairly strong assumption, in fact.
And does it hold in practice?
Well, it depends on the practice, in fact. But we don't have too many. We haven't yet studied the real practical applications.
Mm-hmm.
So, my personal idea is that the connectivity does not always hold in practice. Mm-hmm. But yes, it's a strong assumption. That's what makes it a strong assumption.
And is it really possible to analyze this problem if you don't assume this?
Yes, there is the so-called assumption of B-connected graphs. B-connected means that if you take the union, please correct me if I'm wrong, if you take the union of H sets over B iterations, then to take the union of the edges, you will get a connected graph. That is, for example, a two-connected graph on 4 vertices will look like iteration 1, iteration 2, iteration 3, something else. If I take the union of the H sets here and here, I'll get a connected graph. If I take the union of edges here and here, I think I'll get a connected graph once again. So that is the two-connected graph.
Okay, so another possible assumption.
Yes.
Mm-hmm.
Yeah, I think after that there is many ways you can define that, because you can also define connected in expectation, connected with high probability, connected almost surely. So it's and each one of them requires different set of analysis.
Okay.
So I have one question. So we always assume then worst case condition number of the graph. So
Yes.
the smaller of the mu's, the bigger of the
Right.
the bigger of the maximum graph eigenvalue, the smaller of the smallest.
Yes.
but then you can imagine a sequence of graphs. The first graph is a very bad one, and after that is fully connected. So the analysis here, you always take the worst case. So do you think it's a way we can use, let's say, the current information about the graphs to improve the bound?
I'm not sure, but I think the answer lies in the gossip algorithms. Somewhere we should search somewhere there.
Okay, and the moments of time when the graph changes, you assume that these moments are not random for the experimental setup.
Yes, it just changes at every iteration.
At every iteration of the outer.
Of the outer loop, right. Mm-hmm. So we assume that it changes and then it waits until everyone communicates, then it changes once again and waits until everyone communicates. So during the communication round, it does not change. The communication round is atomic.
Mm-hmm. And in your analysis, the situation is the same?
Yes. So it may change at every iteration. We have another results concerning dual approach, where it changes rarely enough. But these results are, they're completely different.
Mm-hmm. And you use the primal approach here because of this time variant setup?
Yes, because in dual approach, we have two strong assumptions on the function. And there is another paper on dual approach, a recent paper. I'm not sure about the assumptions there. I guess big connectivity, but it's out of the scope. The general idea of this method is to divide the projections, the communications, and finding consensus, and the optimizations and taking gradient steps. And then you can use different techniques for this and for this. And maybe you can get acceleration somewhere.
And do I get it right that you don't control, in this method that you propose, you don't control the accuracy of this projection? You just make some projection?
Yes. From the theoretical point of view, we provide an upper bound on how many iterations we need to make to obtain the desired projection quality. In practice, we just choose some number of iterations for the projection, and of course, in practice, we cannot control the projection quality without centralization.
Thank you.
Once again. Thank you.